Continuing with integrating factors for exact equations, we want to figure out how to find this integrating factor mu of x comma y. All right, so let's start out. Let's say we have some ordinary difference equation, and it's in the format for exact equation, and it's not exact. All right, so then the next step is we're going to take mu of x comma y times mars of x comma y plus mu of x comma y times Neptune of x comma y prime equals 0. So the new condition now is we need partial y of mu times mars equal to partial derivative with respect to x of mu times Neptune. All right, so partial derivatives end up working. They have product rules and chain rules and all that fun stuff. So we're just going to take these here. So I have partial derivative with respect to y applied to this product. It'll end up being partial mu partial y times mars plus mu times partial mars partial y. And in order for the equation to be exact, that's where this equals comes from. I want this equation to work, to be true. So then I also on the other side have partial mu partial x times Neptune plus mu times partial Neptune partial x. All right, so we were given this differential equation in the beginning, we're assuming, so we know what mars of x comma y and what Neptune of x comma y are. So really, we know this piece here, we know this piece, we know this piece, we know this piece. We have no idea what mu is, these four pieces. And so this is actually an extremely difficult problem to solve. It's no longer an ordinary difference equation. This is a partial difference equation. So I have partial derivative of mu with respect to y here, I have mu here, I have mu here, I have partial derivative of mu with respect to x here. It's extremely difficult to solve. So instead, difficult to solve, extremely difficult to impossible. Extremely difficult, let's see, to impossible to solve. This PDE. So then instead, we're going to try and make a simplification. So we're going to hope that mu of x comma y is only a function of x. Meaning that mu of x comma y is really just mu of x. We can drop the y. If that's true, then we'll have this partial mu partial y is equal to 0 because there are no y's inside of mu. And so if that's true, then we take this equation we had before and we end up with 0 times m for the first term plus mu times partial m partial y is equal to partial derivative of mu with respect to x, and actually, so I'll just write that out. It ends up being the normal derivative there. So partial mu partial x times Neptune plus mu times partial Neptune partial x. All right, so first we can rearrange this a little bit. And one thing too, so this piece ends up being just mu prime. Since there's only one variable and it's x, we don't have to write this as a partial derivative, it's just mu prime. And so now if we rearrange things a little, the first thing I'm going to do is I'm going to forget about this 0 times m term, and I'm going to subtract over this partial Neptune partial x to the left-hand side. All right, so if I do that, I end up with mu, and I have both of them now, so I have mu times partial m partial y. And I'm subtracting this mu over, so that mu is going to get factored out, and I have a minus partial Neptune partial x. And left on this side is mu prime times Neptune. All right, so the next thing I'm going to do is I'm going to divide both sides by mu and n. So if I do that, then, and I'm going to switch the sides here. So mu prime over mu is equal to partial m partial y minus partial Neptune partial x over n. If we actually want to solve this differential equation, we know what m is, we know what Mars is, we know what Neptune is, so we can calculate these, we can plug in what Neptune is down here, we can take this thing and we can try and solve it. The thing is that this piece, this fraction, the right-hand side, must only have x's in it when simplified. Right. The reason for that is we have mu prime of x, I'll put the of x here, over mu of x. This thing is a function of x. If this thing has y's in it, it has broken our assumption. We made this assumption, this hope, that we could just say instead of mu is a function of both x and y, it's just a function of the x variable. And so in order for this side to ever be able to equal this side, we need to make sure the only thing over here is x. And sometimes it happens, sometimes it doesn't. All right? But now the thing is, this is actually not a very difficult ordinary differential equation to solve, as long as we have x's over here. So if we integrate this thing with respect to x, it's actually just, so integral of mu prime over mu dx is just the natural log absolute value of mu of x. And then on the other side, we don't know, I can't plug in anything for these since I didn't give you a specific equation, but this is indefinite integral of partial m partial y minus partial Neptune partial x over function n dx. And hopefully it's solvable and we can actually solve for mu, and then we can use that in order to solve to make the equation exact and then solve that new exact equation.